welcome everyone to iClimate Build webinar series. And today we have the topic of an overview of the sustainable eco-design process for energy efficiency construction products. And but before we get started into this topic, we would like to let's introduce a little bit of our iClimate Build project. So, yep, Miguel, you can start.
Yeah, I will present a little bit in 2 slides the iClimate Build project. So this project is related to functional and advanced insulating and energy harvesting storage materials across climate adaptive building envelopes. It's an EU-funded project with a 4-year duration until 2025, and it involves 27 partners from 14 different countries with a budget of 16.4 million euros. So today we will have among these partners from EURECAT from Spain and from Italy, University of Polito. If you go, yeah, so this project is related to an open innovation testbed concept. So we have an entity offering access to physical facilities, pilot lines and capabilities and service required for the development, testing and upscaling of different technologies and advanced materials for industrial environments. And we are working towards a nearly zero emission building concept. So passive technologies for reduction of energy demands and active technologies covering remaining energy needs. So we have already closed an open call that it was related to the project. And we have, as you see here, different building blocks related to materials, to testing, virtual performance testing, safety assessment standards and regulation, upscaling and financing. So yeah, if you have anything related to all these concepts, please contact us through RISE or through the iClimate Build project website. And yeah, now I give the floor to the invited speakers.
Yes. So now, as I mentioned earlier, like we have the invited speakers from our consortium partners in EURECAT and also like University of Torino. So please welcome them. And in case that you have a question, so you can raise your hand or ask in the Q&A or in the chat. And every session we will have the Q&A. Yes, so I give the floor to you, Irene.
Thank you. Can you see my screen?
Yes.
Yes. Okay. Well, I am Irene Raffles. I am an architect. I lead the product innovation and multi-physics simulation unit from EURECAT. And my background is especially in developing new products for construction sector. So my speech will be about how to address new construction product development. A little bit about certification pathway for construction products, and also how iClimate Build project and its ecosystem can facilitate product innovation. This is like a brief introduction in product development and how we think that it's the way to do that. And during all this process, it's necessary to be aware about the regulation and also apply an eco-design methodology to achieve the results, the expected results. So the best way is to identify innovation opportunities, identify market needs, and understand the requirements of builders, constructors, analyze competitors. So the first is a benchmark about market, also be aware about patterns and how is the trends of a market. After that, it's necessary when you have an idea of a new product, do a feasibility study to assess technical, financial, and market viability, and also for sure consider manufacturing and process cost and potential risk, and also during the conceptualization and proof of concept, that is a very important stage of the product development. Generate ideas for new construction product, consider factors such as material functionality and for sure sustainability. And in this point, it's very necessary to be aware about the regulation, because effects could affect the final design of the product and also the entrance to the market. After that, it's necessary to do engineering development and prototyping for these construction products, create prototypes to test the functionality and design of the product. ecological project can help a lot there, because with the open innovation test beds, you can test your products during the design process and during the development process to ensure that you will achieve your results. And for sure, doing laboratory tests at the beginning, during the process, and the end to comply with the regulations. How does regulation impact this process? Well, regulations impact a lot on the construction products innovation process, because there is legal compliance, environmental regulation, certification and testing requirements, building codes, etc. So it's mandatory to consider the regulation from first stage on the project. And for construction products, there is a regulation from European Union, that it's construction product regulation, that is necessary to review at the beginning of the project, because if determine applicability of the construction our new product, how this regulation applies our new product. Could be two ways to assess for our products. Could be that our product it's covered by an European standard, or that we need to obtain an European technical assessment because the product is not covered by an harmonized standard. Harmonized standard, it's a kind of a typical standard where it's all described for testing, and all of the requirements of the product has to comply. It's perfectly described. And if, for example, in innovative products, or in such a kind of facade innovation, innovative products or something, sometimes there are not an harmonized standard that covers these products. So we have to go through an European technical assessments that involve working with a technical assessment body to assess the performance of our product against a specific criteria. And this is an example of an harmonized standard, and this is an example of an European technical assessment here, the generic type and use, and there are a lot of European technical assessments developed, and we can adopt that. Or if our product is not covered by one of the existing European technical assessment, we need to develop one with these notified organizations. And after we do the testing and documentations, we need to apply the CE marking and make a declarations of performance. And how ecological project and its ecosystem can facilitate product innovation. So ecological has pilot lines, so can help us during the development process, for example, doing proof of concept, of conceptualization of new products and testing new materials. Also can upscaling, help us upscaling and do process optimizations. For sure, characterization and testing during all the process, during, for example, lab scale, but also in large scale testing. These are in these open innovation test beds that you can test facade component and a medium scale testing. And also during the process, we can do virtual performance testing, that it's like advanced simulation, multi-physics simulation, or multi-scale modeling, that my colleague Raquel will explain in detail now. during the process of product development, we can test and ensure that all our steps are going to the best result for the project. And for sure, sustainability and safety assessments, this is mandatory, and it's something that we can have to be aware of during all the project. So also iClimate project can help you to do this review of sustainability and regulatory and standards, etc. And this is all from my side. If you have any question, please. No.
So if no questions, so we will move on to the second speaker. Yeah, Raquel.
Yes, I'm now sharing my screen, hopefully.
Yes.
Okay, perfect. Then, as Irene said, I'm part of her team in the product innovation and multiphysics simulation line. Well, I am Raquel, and I'm an engineer, mechanical engineer, with a master's in thermal engineering, and I'm more specialized in the multiphysics simulation part. And this is the my part of the webinar, this simulation, multiphysics simulation capabilities, and how we have applied this to the iClima Build project. So first thing, I don't know if any of you are familiar with multiphysics simulation, but basically a simulation is an approximate numerical solution of all the equations that define the physical behavior of a domain, dividing it into numerous subdomains called finite elements. This can be a bit hard to understand just by this description, but here we have a small drawing that makes it more understandable. So imagine that you have, for example, this square, and you apply a force. Then there are physical solutions, some equations that describe this behavior, no? And then when you apply this force to this square will deform in this way. Okay. What happens if you do not have a square? You have a different geometry, a strange geometry here in the center. There are no equations or analytical solution that describe how this form, this shape will deform. So this is where you apply multiphysics simulations. You can divide this shape into small squares that you know how they behave because you have an equation that defines its behavior, and then solve this equation in each of these squares. And then with this, you will have the final solution or the deformation of this strange shape. This is basically what multiphysics simulation does, but with all the physics that can happen to a part. So this could be mechanical equations, so deformation, for example, but also thermal behavior, fluid dynamics behavior. Well, anything that can be described with equations. So every physics that there is, they can be simulated with multiphysics simulation. And basically multiphysics means that this physics can be combined. So you can have, for example, in this first video, we have a stamping process. So there's this metallic shell that, if I can make this work, yes, you can see that in between these two other parts, it deforms, but also this scale is temperature. So it deforms with temperature and it cools down once it's finally in its final shape. Another example could be this one. This is a fluid dynamics example. This is a windmill. if a vertical blades windmill, if you look it from on top. So here you can see the air moving and the blades rotating. The other example, this third one, this is a machine, well, at the end of the machine, that has some particles. It's a particle distributor. You can see these red dots that follow this path, and they distribute between these tubes. And the final one is filling, mold filling. For example, high pressure casting. Maybe this is aluminium, it can be plastic, anything. It can be simulated, the injection of this material into a mold. So the simulation process has different parts. There's a strategy. You have to start with a design. This design can be, usually is created with CAD software, for example, SolidWorks, CATIA, any of these design softwares can provide a CAD. It can also be generated via other software, for example, generative design or mesh treatment, but the usual is you have a CAD part. Then this CAD part you insert into the simulation software that can use different methods. The more usual ones are the finite element methods or computational fluid dynamics, depending on the type of simulation that you have to do. And then the process can stop here, but sometimes you can go even a step further and you can do some optimization simulations that can be parametric or non-parametric, depending on the type of application that you have. Here we have a very simple example. The design part would be, for example, this part, which is a CAD drawing of this bracket that is made by some material and has some properties. For example, its weight. Then this part you can assign some loads. For example, that this can be screwed down somewhere and has some loads on top. And then you have these profiles that could be, for example, stresses that this part is suffering. And the other type of simulation or final part of this strategy could be the optimization. So you could do a special type of simulations, which are topology optimization, where you say, well, I have this part, I have these restrictions. For example, it has to be screwed down in this part and has to have a hole here to do something. Please optimize this so that its weight decreases, but it's able to withstand the same stresses. So the simulation software would remove material and generate a new geometry that accomplishes all these constraints, but with less weight. So this is a special type of simulation that sometimes can be done, but usually we are focused on the middle section, the finite element or computational fluid dynamics. So as a summary of simulation and also EureCAD's capabilities, we have the strategy that I was explaining now, design, simulation, and optimization. We have the scope, so these simulations can be applied to a lot of different things. It can be applied to product, as I will show you now from the iClimaBuild project, but they can also be applied to processes. We've seen stamping, we've seen mold filling. So these would be processes, and also to different topics. So construction, which is the main topic of this webinar, but also digital twins, electric batteries, hydrogen, or many others, for example, health. So, well, basically anything. Physics, the usual are mechanical, which you've seen also an example on the bracket, thermal, which you will see now from the iClimabuild project, fluid dynamics, that you can also see now, and electrochemical, for example, for electric batteries or hydrogen fuel cells. And also we have a lot of software, which is commercial software validated by industry to do simulations. We have the more important ones or more used ones, which are ANSYS and Abacus. ANSYS that can do both mechanical, thermal, fluid dynamics, chemistry, anything. And Abacus, which is very powerful in mechanical simulations, vibrations, and all these kind of things. But then we also have Tosca, which is for optimization, Procast, which is more specific, Moldex, and then all these CAD software, SolidWorks, CATIA, and Grasshopper, which you probably all know already. So focusing on the construction simulations that can be done, there are many types of simulations that could be performed, but basically the more interesting ones we think that could be a structural analysis. For example, here we have a structure with some loads and you want to know if it resists, if it doesn't break. So this could be a structural analysis. Failure analysis. So you want to see when it breaks and how it breaks and with which loads or restrictions need to happen for this to break. Topology optimization applied to something more construction-like. This is a beam. So you can have this with beams, with bridges. Also fluid dynamic analysis, you will see one now from the iClimabuild project, but this could be another example. Aerodynamics of something, a city in this case. Thermal analysis, for example, thermal bridges in a window, and modal analysis, which would be vibration analysis, for example, in this case, to a bridge. So focusing on the iClimabuild project, in the test case 1, there's this heat exchanger, PCM heat exchanger that is being developed. This will be attached to a window where my colleague Ginevra will explain probably better. So this would be attached to a window, and its use would be to make sure that the temperature that the room receives is okay and is adequate, has its adequate conditions. So to this heat exchanger, some air will enter from the window or outside air, depending on the situation, and then it will go through these 5 plates of PCM, which melting temperature is 21 degrees, and then it will go out of this heat exchanger and into the room where this is installed. So to verify that this design was correct and was good and its behavior was working as it was intended to work, a simulation was done. This simulation basically takes into account 48 hours. So we have 2 days of this heat exchanger behavior. The inlet is this temperature that comes from the window, and it was done by another simulation by Polito. And then what we have is the behavior of this heat exchanger and also the temperature at the outlet, which is the inside of the room. So first results would be these velocity streamlines where we see this air inside this heat exchanger. So we see here that there's these two blue squares are the inlet, which are two fans. So we have these lines flowing from inlet to outlet, and they go through in between these 5 plates. So we have here these two sections. We see the air going around these 5 plates, which is what we wanted. We wanted for the air to go in between these 5 plates and be the more homogeneous as possible. And if we see this on top, we have the same. There's the air occupies mostly all the space available. Of course, there are some local recirculations in some areas, for example, here and also here due to the design. Here we have two videos. First one is temperature distribution. So you will see now once I click play that first temperature is cold, then it becomes hot because the inlet temperature increases, and then the night hits, so temperature falls again and then increases again in the second day. So let me see if I can play it again. So you have cold, then high temperature, then the night it gets cold again, and then temperature increases again with the following day. And then on the right hand side, I will play it again. You have liquid fraction. So the melting of these PCMs. When the PCMs are blue, it means that they are solid, and when they are red, it means that they are liquid. So you can see that during these whole days, the PCM has not fully melted, so it's always in the melting. It's mushy, so this is what we wanted to have the for its behavior to be as we wanted, to have the temperature inside always constant. So here we have more results of the same. So in these lines, the important line to look at is this blue line, which is the temperature at the outlet of the heat exchanger, so inside the room. So we can see here that the temperature starts at ambient temperature, and then it increases with the for the PCM, and then it remains constant or almost constant for the whole duration of the second day, which is what we wanted, that even if the temperature outside is low, so this green line is outside temperature, is low, inside the room we have 20 degrees. So with this, we have verified that the PCM works for this application. So this heat exchanger can be a good idea for this application. And then on the right, we have some time frames of the videos that I was showing earlier, so at different times. The temperature behavior and the liquid fraction. So we can see, for example, on the 40 hours, that the liquid fraction is always some percentage of it is fully liquid, but the remaining is not melted yet. So this is what we wanted, always to be in this melting process so that this temperature can be constant. And we can see that with the simulation, it verifies this. And so we can see that in this test case, we have verified virtually the behavior of this product that we have designed in the iClimabuild project. So with this, my presentation is complete. So if you have any questions, so please go ahead.
Thank you, Raquel. The audience, if you would like to ask the question, you can raise your hand or you can type it in the chat. Actually, I have one question. I don't know, on slide 6 or 7, you show the velocity of streamline occurring on the PCM heat exchanger. How do you think the design could be modified or improve air behavior inside the device?
Yeah. So as I've said before, we have some local recirculation areas. For example, these blue lines that are like a circle. This area here, also this area here, and on the other view, also on top. So ideally, we would like to eliminate this area because these areas means that the air is recirculating and heating itself up, which you don't want this. You want this, you want the air to go through. So probably I would just eliminate this corner and make it like on the end that you have this inclined wall. I would do the same.
Yeah.
On this inlet part. Also another thing that could be done, but this would be major modification, is to change the size of these inlets and make them occupy the whole volume, but this could have other implications. So easier modification would be just to make this slope.
Yeah. And I have another question on like the time frame of when you do the simulation. Like how do you define that you will run the simulation for 2 days, or like you can do it longer, something like that? Like, yeah.
Well, we decided to do it for 2 days because if you see here on the final results, you can see that on the first day you have the result is conditioned by the initial conditions that you have put. So we wanted to do this for 2 days. So the second day is not as conditioned for the initial conditions applied to the simulation. Ideally, you would run this for more days, so you would see the tendency. However, these simulations are very long to calculate. So yeah, so we decided that 2 days was enough to have an idea of this working or not. Also, we knew that some experimental testings would get done. So now we will have more information besides simulation to verify the behavior of this design.
Okay, so when you run the simulation, then later on you compare with the testing result, right?
Yeah,
to
exactly.
Verify it. Okay.
Yeah, it's not explained here, but we have done this.
Yeah. Okay, thank you. So any other question? Feel free to ask. And if not, next presenter is Ginevra, right? Yep.
Okay. Welcome to everybody. I'm Ginevra Di Castri and I'm a PhD student in energetics at Politecnico di Torino. I've been working on the European project iClimabuilt on several tasks with my research group. And today I would like to talk about the test case 1, which was introduced by Raquel in the previous slide, to be more precise about the development of a mathematical model which could represent a PCM-to-air heat exchanger. Before going into the mathematical model, I need to introduce to you the reason why we needed to develop such a model and also the components that we are studying. We focus mainly at component level, and our aim for the eclimabuilt project test case 1 was to assess the performance of the component I will introduce to you at building level or room level. So the component is an advanced fenestration system, which is made of a double skin facade, which is this glazing part, and a PCM-to-air heat exchanger, which is, of course, the same PCM-to-air heat exchanger showed by Raquel. This advanced fenestration system, it has two openings in the bottom part and in the upper part. Here we have some fans in order to take the air from the outdoor environment. The air then is able to flow inside the glass skin. Thanks to the solar radiation, the air inside can be preheated and can go inside the PCM to air heat exchanger thanks to other fans that are located here. Then, after going into the PCM to air heat exchanger, it can flow inside the indoor environment. This system is very innovative because most of the time, double skin facade don't have a PCM or another kind of heat exchanger. And what happens is that when the air is preheated by the solar radiation, can reach very high temperature. That, of course, are not good for the indoor environment. Because if I introduce air at, for example, 30 degrees inside an indoor environment, I will have, of course, thermal discomfort. So the PCM to air heat exchanger is a very innovative component because it can lower the temperature of the air during, for example, summertime or wintertime if the air is preheated too much. So our aim was to do the optimization of the design of such a system, and also to assess the performance at building level of this system. To do that, we normally use building energy modeling software. One of the most known, for example, is Energy Plus. The issue of this work was that, first of all, it's not possible to model a component such, for example, PCM to air heat exchanger in building energy modeling software because they are too complicated. And also CFD, which is very precise, as we have just seen, cannot be integrated inside the building energy modeling programs. So our aim was to develop a flexible model of both the double skin and the PCM to air heat exchanger that can work independently in each part in order to do the optimization of the design of each part, and also as a whole in order to connect the entire system to a room or a building, for example, and assess the energy, but also thermal comfort and visual comfort performances at building level. So to do that, as I said at the beginning, we decided to develop the PCM to air heat exchanger as a mathematical model. We did that in Python just because it was the most flexible interface to use, and the mathematical model was implemented as a node finite difference model. So what we did was that we, of course, did some assumption, for example, compared to CFD, like, for example, we decide that the air will distribute in the entire PCM to air heat exchanger equally. And we took an infinite element of this heat exchanger. Here we can see the two plates of the PCM and the air flowing in. So we took an infinite element. We made the heat balance at this element, and then we developed the solution of the governing equation. By doing that, we were able to calculate the air temperature at the exit of the PCM to air heat exchanger, the PCM temperature, and also the heat exchanged between the air flowing and the PCM plates. When it comes to mathematical modeling, of course, we need to make sure that this mathematical model is working properly, so the calculations are right. In order to do that, we decided to compare our results, so the results of this mathematical model, to other results that were reliable. Firstly, we did that by comparing our results with some experimental results that we took from literature. So here we can see that we set, of course, the same boundary condition in order to make the exact same simulation. Here we can see the comparison between the outlet temperature of the experimental results, which is the yellow line, and the outlet temperature of our mathematical model, which is the blue line. In order to understand the difference between these two models, we calculated several metrics, as you can see here. The coefficient of variation of the standard deviation, which give us a measure of the variability of the differences between the model prediction and experimental numerical data. And the lower it is, the better it is. The coefficient of variation of mean square error, which give us a value of the difference between our mathematical model and the reference model, so the benchmark. And the normalized mean bias error, which give us an information of the bias in the model. Following the Ashray standard, the first metric has to be lower than 30% when we talk about hourly simulation, like in this case, and the last metric has to be lower than 10%. So these results were quite good. Then we decided to having this partnership with the Eureka Research Center. I had the possibility to work with Raquel, and we compared our results of the mathematical modeling with CFD results that they made. And here we can see the same graph that Raquel was showing. So we have a 48-hour simulation. The yellow line is the outlet temperature of the air at the PCM heat exchanger with CFD results. And the blue line is our mathematical model. Again, this simulation is very good because it lasts more than the previous one because it's for 48 hours. So the behavior of the PCM can be kept better, and the temperature at the inlet of the PCM to air heat exchanger goes from 15 degrees to 48 degrees. Again, the results of the metrics were similar to the experimental results and were quite good. So what we can say is that our mathematical model was relatively accurate in predicting the experimental results, but of course we want to lower the metric value even more to have a more precise model. To be more precise, what we have seen, especially with the air temperature, is that we have a maximum difference of plus 0.8 degree and a minimum difference of minus 0.8 degree, which can be acceptable, of course, but it also depends on the indoor environment's requirements. So this is why we want to make this model even more precise. So as future work, what we want to do is to calibrate our model even more. In order to do that, we need a massive data set, especially it would be perfect to have experimental data in order to do that, which has to be for long-term monitoring data with different PCM melting temperature and of course with different boundary condition like environmental condition. To be more precise, thanks to the iClima built fundings at Politecnico di Torino, we are already doing that because we were able to install the system that I presented at the beginning. So this is the window part with the two openings, here the bottom part, and here we have the upper part. And here from the inside of the testing room, we have the PCM to air heat exchanger. Thanks to this test case, we are monitoring all the experimental results, and we are trying to calibrate our model even more to make it more precise. So for me, that's all. Thank you for your attention. And of course, if you have some questions, I'd be glad to answer.
Any questions so far? If not, we move on to the next presentation. So thank you, Ginevra, and welcome, Carolina.
Hi. Can you see my screen?
Yeah, now, yes.
Okay, perfect. So I'm Carolina Villa. I'm working in Eurecat with Irene and Raquel and Regina, but in a different area. And I'm going to present my presentation is a little bit different. It's about life cycle assessment and eco design. And okay, I'm work in Eurecat, but in a different department. I'm working in the Sustainable Impact department. And here we work with a different methodologies like life cycle assessment, life cycle costing, social life cycle assessment, safe and sustainable by design framework that also includes the safety in the design perspective, consequential LCA, material flow analysis, corporate carbon footprint, and so on. And we apply all of these methodologies in design for circularity, eco-design, in reduce water footprint, carbon footprint, and so on. More or less, this is our area of impact. And following this, I'm going to put the focus more in life cycle assessment and eco-design, because why is so important to change the way that we understand our products and design them in a more sustainable way. There are many reasons. For example, the effects of climate change that we are seeing every day, among others. So, so to curb the negative consequences of climate change, the European Green Deal was launched with the objective through different policies to reduce net greenhouse gas emissions by at least 55% by 2030 and to be neutral by 2050. Also, under this objective, a Circular Economy Action Plan was launched in 2020 with around 30 action points, among which were, for example, ensuring the development of sustainable products and circularity in the production processes, empower consumers with more information and more transparency, also targeting key sectors as, for example, the construction and building sectors, but also batteries, packaging, textiles, plastics, and more. And also reducing waste and more actions, but putting the focus in the circular economy strategies. And how does all this affect to the construction sector? Well, as I mentioned, this is a key sector and it is responsible for 50% of resource extraction and consumption and 40% of European energy consumption. And for this reason, in December 23 last year, the Commission proposed a provisional agreement on the revision of the construction products regulation. And with this agreement, they want to manufacturers will have to provide environmental information about life cycle of products and design and manufacture products in a way that facilitates the reuse, the remanufacturing, the recycling of these products, give preferences to recycling materials, make available instructions on how to repair these products and how to use better. And okay, last but not least, on December of the last year, also the Council reached a provisional deal on new eco-design requirements for sustainable products. Establish, for example, the digital product passports for provide information about the product's environmental sustainability. And also, on this February, the Council also reached a provisional deal on right to repair directive. And the main elements of this directive are the right for consumers to request manufacturers to repair products, and online repair platforms to connect consumers with repairers, an extension of 12 months of the liability period of the seller after the repair of a product. So as you can see, all these changes are becoming more imminent and more important. And taking all of this account, how can we ensure that the products already on the market meet these objectives? Or how can we ensure that future products to be released already take all of this into account? And this is where life cycle assessment and eco-design of products can help us. So first, let's see the life cycle concept. In a biological, in biology, a life cycle represents a series of changes that an organism undergoes from birth to death. But applying this approach in business, the life cycle represents the entire existence or life of something in the marketplace. This includes products, services, business, buildings, from raw materials to production step to warehouse, to the use phase, and also to the end of life. That if we are able to recover or recycle this product, we can close the loop, and this product can start another life in another loop. But in each of these steps, you have an environmental, economic, and social impact associated. So under this life cycle concept, the life cycle assessment tool was created to calculate the environmental impact of each of these steps, quantifying the inputs like reagents, materials, chemicals, also the outputs of the system like emissions, the waste generated during the process, the fabrication product process of the product under the scope, and so on. And also using these standards that you have here, and so that we all follow the same rules, and also because if we use the same rules, the objects that we have the same use and are analyzed under the same conditions can be compared. So this methodology, applying this methodology, you can compare some products. Also, this type of assessment is the basis for the environmental product declarations that maybe you already know. And one thing that is important is that you can apply this methodology also for buildings. And you can apply this methodology from cradle to gate, for example, from the raw materials to the manufacturing stage, or from cradle to grave. That means also the end of life of that product, or from cradle to cradle. That means that you don't have a waste, that you can close the loop of your product. And following this approach, why life cycle assessment and what for? So for example, to quantitative assess the impacts of your product, to have more knowledge about your product, but also to identify some hotspots that you can have in your product in order to avoid these hotspots. But because if you know and if you have information about that, you can act. But first, you have to see where the impacts are, in which step of the cycle. Also, well, as I said, it's a good tool to implement reduction plans, but supported by numbers. Also to make sustainable claims, because with the new law to combat greenwashing, you have to prove that your product is better than another product. And for do that, you have to know your product and have data, environmental data, to prove that your claims are true. So this tool is a good tool to do that. And also because it's standardized, we all follow the same rules. And well, there are many rules also if we talk about environmental product declarations and so on, but we work under the same rules. Well, and also there are some limitations, because for do this kind of assumption, for this kind of studies, you have to do some assumptions, and also could be some uncertainty inherent to life cycle assessment. But you can combat this uncertainty, and also it's important that this type of studies are it's a tool for estimating potential environmental impacts and comparing alternatives, but not to predict the actual impact that will occur in that product. That means that we can calculate that the impact, but some stages of this life cycle could be different. For example, if you during the use phase of your floor clean more than we put in the assumptions, of course, the actual impact will be slightly different, but more or less it's a good approximation. And well, here we have an scheme of the 4 main steps of the life cycle assessment. First, we have the goal and scope definition. Here we determine the purpose of the study, the scope, what is included and what is excluded, the system boundaries. For example, if we are conducting this type of assessment for a building or for a solar panel, you have to define your functional unit and of course why you are doing this study and what impact categories are you going to use, and so on. The second step is the inventory analysis. We collect all the data from inputs and outputs of the system and the energy consumption. And with this data and the functional unit that you use, we see if the data meets enough quality, if the allocation factor is correct, and so on. And then with this inventory, we perform the impact assessment step. That means that you assign to this input and outputs of your inventory an impact. Normally we use, you can use a lifecycle assessment software like CIMAPRO, Gavi, or OpenLCA to do that. And with that, well, also here there are some information about the impact categories that you can analyze and how the information is provided by characterization factors. Here you have an example of depletion of abiotic resources and also about climate change. We use these factors and we put this factor with the specific input to see where is the impact. And then the final step is the interpretation of these results. And here you can evaluate what's happened with your product, where are the main hotspots. Also, you can do some sensibility analysis to see what's happened if this product, okay, for this specific product, we are using the electricity mix of this country, but what happened with the use phase of this product if we sell this product in another country, for example? You can play with that, or what happened if we change this material that have a lot of impact. For that reason, as you can see here, the arrows of the process are bidirectional because it's an iterative process. If you find a hotspot here, you can come back to your to your assessment and change the things in order to obtain the best study and the best performance for your product. And with all of that, you can obtain some conclusions about your product. Here you have an example of the product results that you can obtain. This is for a construction product. And you can see the results for each of impact category analyzed. There are a lot of impact categories, but we decide for that product use these ones. And also for each specific stage of product. For components manufacturing, transport of components, manufacturing stage, distribution, use phase, and end of life. And for example, for global warming potential, the carbon footprint, you can see that the highest impact is in the components manufactured, but also the use phase has a lot of impact in terms of CO2 or the end of life. So once you have more information about your product and you know where are the impacts, you can start to do something. So here you have the different stages of the life cycle assessment. And when you identify the hotspots, you can see, okay, let's do something. Let's put together the life cycle assessment and the eco-design methodologies to improve my product. Because to decarbonize the construction sector, it's important to put together these methodologies in order to have a entire life cycle, have a entire understanding of your product. Okay, so then we now know how to apply life cycle assessment. Let's see what's happened with the eco-design. According to the European Environmental Agency, eco-design is the integration of environmental impacts aspects into the product's development processes by balancing ecological and economic requirements. That means that we can use these eco-design principles in order to minimize negative environmental impacts in our product, but without compromising the quality of our product, the function, and the technical performance. So the eco-design principles could play a pivotal role guiding the development of low carbon alternatives, optimizing material choices, and enhancing overall resources efficiency. For example, here we have an example that a work that we do for the result that I already showed. We found these different hotspots. For example, as you said in the results, the impact of the materials, of the raw materials stage was very huge. So we propose that change the materials with more impact with another alternative with lower carbon impact. For example, for PVC parts, maybe we can change this PVC part for polypropylene. What's happened with the impact? Or with recycled plastic, let's see if the impact is lower. Also, we saw during that assessment that the impact of packaging was huge. Okay, then let's go to propose and packaging optimization. Maybe we have to act first if we want to reduce the carbon footprint of our product. Maybe we can start reducing the size of our box, or maybe we can change the main material to use more recycled percentage of plastic in our box. I don't know. The idea is to see where the impact is. In this case, for example, the impact of packaging was huge. Let's see what we can do to reduce this impact. Or, for example, we see that when we propose a value chain optimization, analyzing the different suppliers and see which one is better in terms of sustainability and also in transport and so on. You can do a lot of things, but first you have to know and to have the environmental profile of your product, and then you can act and do things in each of these stages. We also propose some things in energy efficiency and system automatization, comparing energy performances of the product, and see what we can do in end-of-life strategies and so on. And well, with that, you are able to provide some recommendations. For example, some of the other actions that you can put in practice is, as I said, packaging optimization, using sustainable products, or add information in your product itself using digital passports, or in your product with a label in order to know more about your product, also about their carbon footprint, but also maybe with the construction instructions that will help to the final consumer to do a better use at the end of the life of your product, and to ensure the recyclability of your product, or also using reducing the restricted hazardous substances, or design for disassembly to in order to obtain lifetime extension, or to ensure a second life of your product, or using responsible sourcings, avoiding the use of critical raw materials. You can do a lot of things in order to improve your product once you know where the impacts of your products are. Also to to increasing the reparability of your product, the recycling, the reuse. I don't know, this is just an idea that what you can do with the information provided by the life cycle assessment. Also, we can do sensibility analysis to see how we improve each stage. But this is a study, this type of studies have to be together by subsequent work with the production team to see if the changes that are made are technically viable or not. So it's a good starting point, but you have to combine these actions with a specific strategy, readapt the current technological aspects and the current strategies, and then implement actions. So you have to combine this information that we provide with the life cycle assessment studies, with your technical team, in order to address the environmental perspective of your product always, and to be able to provide this environmental impact reduction, but without compromising the technical performance, of course, because if you can change this part with another plastic, because maybe the new plastic it doesn't have the requirements that you need, it's not okay, it's not possible. Let's try to do it different. So we think that it's important to keep this in mind, and with that, using the life cycle assessment and the eco-design actions, you can reduce all of the impact categories that you want to reduce. For example, in this case, with these eco-design actions, you can reduce the climate change in a specific percentage. Okay, so for this is I'm almost done. For that product that I already showed some results, we implement all the actions that I already showed you, and we obtain a reduction carbon footprint of 34.5% of the carbon footprint. But this was an existing product. What happened if we use this concept, this life cycle assessment plus eco-design, in a new product that it's designed from the beginning using this eco-design criteria? You can avoid for sure most of these impacts, because it's more difficult to implement these actions in a product that is already in the market. It's more difficult than in a new product. But you can see that even if the product is in the market, doing some small changes during the life cycle assessment of this product, you can reduce a lot their impact. So, and maybe you think, okay, it's not so much, 36 kilograms of CO2, but if you, if during a year you produce 100 units of this product, you can assume that the carbon footprint that you reduce, we are talking about tons of CO2, not only kilograms. So in conclusion, well, sorry, I'm finishing. In conclusion, so by integrating eco-design principles and life cycle assessment into the construction products development process, we can pave the way for a more sustainable and environmental conscious future in building sector. Thank you. And well, if you have any question, please let me know. You can also send me an email if you have further information. And that's it from my side. Sorry, because maybe I take a lot of time.
Oh, no problem. We still have time, and we still have time for the question as well, if you have. So yeah, I see one question. Yes, in the chat. The terrestrial ecotoxicity assessment includes analysis of alerts that affect persons or the impacts on persons with multiple chemical sensitivity disorders.
Normally, if we need more information in a specific impact category, we can check now. I don't know if this is a specific included, but if it's not, normally we do a specific study about that. And now with the new Safe and Sustainability by Design framework, all of this is included, because this framework wants to minimize all the impacts in human health, but also during the production of the processes. So if it's not included yet, it will be when we will use the Safe and Sustainable by Design framework. Sorry, because I'm not, I don't have the specific answer for your question, but I hope my answer helps.
Okay, thank you. Any more question? Anyway, you can contact all the speakers after, because I think they put all the contact info after their presentation. So if there is no question further, I will move to our last presentation from Regina. So welcome, and thank you, Carolina.
Hello, my name is Regina Enrique. I work at the Applied Artificial Intelligence Unit at EURECAT, and my presentation will deal with advanced simulation and the merge of data models that can be the mathematical models presented by Raquel or Ginebra, or data-driven models, and the concept of digital twins. It's true that it's not specifically focused on the eco-design process or on the design phase, but covers the broader scope. By the way, I'm a telecommunication engineer, and I work in projects related to optimization, forecasting, anomaly detection, recommenders, and specifically in different fields, but basically in the energy sector and also in the electric mobility sector. So I will start with a brief overview of our unit, what we do. the concept of digitalization, that is the basis for all the rest that I will explain, a little bit about interoperability and its challenges, an overview of the digital twins and specific applications using AI, and what are the challenges. So at AAI, what we do is apply data analytics, machine learning to solve problems linked to industry, water and energy management, agri-food, also environmental climate change, and of course construction. And what we do is to develop tools to optimize, for instance, the industrial processes, to applications for smart maintenance, to optimize workforce, but also to do digital twins and prescriptive management. And our main inputs are data, and what we try to do is extract information from this data so that it can be transformed into actions, or at least informed decisions. So by analyzing the data, we can know, or we will try to know what happened, but also why it happens. And the most advanced applications are, okay, then what will happen if you don't change it? And finally, what can we do to improve things? It's true that we hardly ever, at least in this kind of European projects, reach the automation stage, because before we reach that point, it has to be a lot of trust and a lot of trials and a lot of monitoring. So the basis of all that is data, and data comes from digitalization and what we call at some point industry 4.0 has its main key enabled technology in the digitalization, as the steam has in the first revolution with mechanization, and the second revolution with electricity. And now, apparently, we have overcome already the Industrial 4.0, and we are in the fifth revolution, and that is characterized by personalization and humanization. And some authors include sustainability, and I agree with that. I think that should be a key in the future. So why I speak also about industry and not about construction, it's because also construction is more and more industrialized every time. So the roadmaps go kind of in parallel. As I mentioned, the data is the basis of everything. So that means that and specific digital data that are ones and zeros, streams of ones and zeros that are gathered by sensors in the field. And this data is then sent to gateways. And these gateways, basically what they do is they compile the data and then send it further away. Or not so far away, but they send to other equipment. And in this equipment, maybe in the cloud or maybe in the edge, if it's local, they are processed, and some decisions are taken, and this decision comes to the field again in form of actions that are implemented by the controllers. So the digitalization process, what involves is the part of the sensing, having sensors that can be more or less smart and can be IoT or can be more conventional sensors that are the ones that are acquiring the measurements or the variables of interest. And this information is sent to other systems. And also this part of the communication is very important because it has to be efficient and especially secure. And then once we have the data in the units that can process them, they are analyzed. And with this analysis, they can extract recommendations or actions that have to be implemented and are able to improve processes. The second aspect, we have now the data, we have the digitalization part. So that's the first part of the digital twin. And now it comes to interoperability. And when we talk in the construction sectors about digital twins and interoperability, the first model that is mentioned is the BIM model. I would say that's not mandatory, but it's a big basis because what BIM is the building the building model that it's mainly the basis of the all the digital solutions, and what enables is to so that many stakeholders in the construction environment speaks the same language, and that's the basis for each other to understand. And in other words, it enables interoperability. And also because BIM has several dimensions, not only the 3D geometric dimension, but also other layers that enables to manage the building from the design until the dismantle of it. And also because it provides a common name for all the objects, instances, and data models. And that's very relevant in an environment where many stakeholders with different backgrounds and tools have to interact. But also we talk about interoperability, not thinking on software or on machines. That's the machine-to-machine interoperability of communications, but also it has to be an exchange of information between the machines and the humans. So here we talk about human-machine interfaces, and we talk about user experience. And every time the interfaces are more sophisticated, and they're not limited to screens, but also they include wearables. And with the real information, we can add also virtual reality. So now we have gone through the part of the digital, and now we are going to the twins. So what's a digital twin? And here we have 3 examples of applications that I hope, after some slides, we will be able to define if there are digital twins or not. The first one here on the left is an image of classical simulator, like the one that Raquel presented previously. The one in the center is a SCADA system, and the one on the right is an application that can be a domotic application for monitoring the some variables on a building, for instance. So what's the formal definition of a digital twin? A digital twin is composed by 3 key elements. One is the real world entity, but it's important to notice that can be a physical element, but also it can be a process. Then we have the virtual representation of this entity of process, and then we have data that connects the two components. And here there are something worth to mention. First is that the 3D representation, it's nice, it helps in this user experience, but it's not mandatory in a digital twin. So that means that a very nice 3D representation of a building does not mean that it's a digital twin. And for instance, you can even have no graphical representation and have all the data in a database. And if you implement the corresponding tools, that also could implement a digital twin. And the second one is that the real model and the virtual representation has to be synchronized. And quite often it says in real time. And here it comes. What does real time mean? Every second, every millisecond, every hour. And this depends very much on the application. So what I think can be concluded that it's mandatory is that the virtual representation is synchronized with the real world entity, and it represents with high fidelity the real asset, but doesn't mean that it has to be synchronized every millisecond. It will depend on how fast this entity changes. And it's quite typical to have images of airplanes because the concept of the digital twin was first used by NASA to model the behavior of the engines. That otherwise it was very difficult to test. So what are digital twins for? And we think especially on a building in this case. Okay, we have the representation of the building that can be in BIM model or in another type of modeling. And since the design phase, we already have this representation of this building. So we can handle digital twins from the design phase to the dismantling of the building. And also we can model not just the building itself, the physical model, but also the construction process. So, okay, then we have with the modeling, we have the replica of the building. And now what is key in the digital twin is that we can simulate what if scenarios, meaning that what will happen if we do this, and that will help us to take the decision and say, okay, I can experiment on my virtual entity, and then according to the results, I will implement in the field or not. And here is where it comes the decision and how we implement these what if scenarios is where the simulation comes in place. And also here we have two different alternatives that are complementary. One is, okay, we can do this simulation or this calculation based on data-driven model, and that is if we have data to do it, or we can do it based on physical modeling if we are at the design phase and we still don't have this data. So here is where hybrid models or the complementarity between the multi-physics modelers or the mathematical models and the data-driven models are combined and can be helpful depending on which situation. And according to the result, in this case, it's an example of if it's worth to install a PV panel or not, then I can decide to install it in the building, I mean in the real entity. And then with the digital twin, I can monitor the power production and see if it's what I suspected, or for instance, there is some failure in the system and I can detect it quite rapidly. I'm not participating, I'm and my unit as well is not participating in Climaville, but we have participated in another European project that was called Sphere, and there also we cover different stages of the construction process, and in particular we implement an application that we call ePredict, and was an application that applies predictive maintenance to the HVAC system. So what is the advantage of predictive maintenance is that it reduces the unplanned downtimes that in some circumstances it could be really annoying. But also if it's in an industry, it's really critical. And even if the HVAC is not breakdown, also it can lead to loss of comfort and loss of efficiency. That's also important because when we design the system, we have you have explained that in Climabuild we are focusing on passive and active systems, and it's good and it's necessary that they are efficient, but also they have to operate in an efficient manner. And so by monitoring this, we can realize if it's the case or not. And then the result can be integrated in another system like this computer maintenance system. That means that an digital twin, it's not starting from scratch, but it's a kind of umbrella that merge different systems and interact between each other. So what is the data-driven modeling process and how it differs from the mathematical modeling? And here is an example of a predict, but it applies to any AI model. And it goes starting from the data sources. We have to go through a process of feature selection. That means that we choose which variables are relevant, and that can be primary variables or some ones that are composed variable, meaning that we perform some operations between with that. And then we have to choose the algorithm, and there are multiple algorithms. And for instance, there are regressors, neuronal networks with different complexities, etc. And then even when we choose this algorithm, we have to choose the parameters of these algorithms. And then it starts an iterative process that it's called the model creation or the training. That means that with the inputs and the model, we try to emulate the real output, and then we iterate until we are satisfied with that. And once we have that, we say that we have the model. And how we will use the model is to predict what will happen in the future, or to see if what is happening now is according to what we expected or not. And that's basically the basis of the anomaly detection. In general, this process is quite long. It depends very much on the complexity of the process and on the knowledge we have in the field. And sometimes the training also it takes some time, a long time, depending on the data we have. But then the prediction of the use of the model is pretty quick, and that makes it suitable for real-time decision. But we can go beyond just predictive application, and we have also many applications of AI in the buildings. And for instance, in NZ buildings, we have to deal with the optimization of the local generation, forecasting what will be the demand and the production for the next day. For instance, if we start introducing electric vehicles also as part of a building or a surrounding space around the building, we have to manage this charging of the vehicle, or the vehicle can support also the power supply of the buildings. But also we can optimize the environmental impact of these buildings with the surrounding area. And finally, or not finally, but one other aspect is that we focus, when we talk about efficiency, we focus very much on energy, and more specifically about electricity. But there are other resources that are also where to manage, and that, for instance, now in Catalonia, we are quite aware because we have a severe drought. It's about the water and also the water and energy nexus. And if we go beyond the building itself, the building interacts with other buildings and with the city and the district. And also we have this concept of the local energy communities. So again, we have more complexity that can be dealt with tools like AI and digital twins that are the bidirectional exchange of electricity flow between the building and the network. Also, we have other concepts like consumption disaggregation, meaning that not all the laws behave the same or have the same flexibility. And also, in the design of the community itself, we can use tools to optimize that. But also beyond the operation and maintenance phase, AI and data-driven models can help in the part of the design and the construction, for instance, for the task of optimization or the task force optimization, and also in the part of the demolition phase, they can be used for the material traceability and finding or improving the circularity of the process. And I mean, this is a kind of a combination of different things. It's not that AI replaces the multiphysics simulation or the traditional systems like SCADAs, for instance, but it's another layer that adds new functionalities. And also it's possible because if everyone speaks to each other. So the main challenges of digital twin are the data. I mean, without data, we cannot do anything. And this data has to high quality, and it's not always the case. So what I learned is that if you have ravishing, you will have ravish out, no matter what functions you apply. So in all these cases, there is also always a phase that is quite challenging. That is the data processing and making it of high quality. And also some data analytics and technique helps on that, but it's a process that cannot be avoided. Then a second challenge could be connectivity, because the assets can be more or less spread, and also they need to communicate maybe from one remote place to another, and also because there are existing systems that can talk with other languages. The third challenge is our silos in two senses. One is the silos between the systems of the software application themselves, because they are from different providers, they have different protocols, and some of them are not open. And I think that's something to take into account when purchasing a new solution. And also the silos itself, that the companies or the entities participating in the creation of a digital twin, they have themselves, so that some departments don't talk to the others, and so the information is quite fragmented. So when trying to build a digital twin, I think it has to change this mentality and find a collaboration environment. And basically, that's all I wanted to explain today. I don't know if you have any question.
Yeah. Any question? I may ask one quick question. Can we build a digital twin for an existing building if we don't have the BIM model?
The answer is yes. We can have a digital twin without the BIM model, or we can build a similar approach to BIM using different techniques, and there are ones that are basic and the others that are really fancy. So first, okay, we can use the 3D dimension, and that we can obtain either because we have like the plant, but also there are other sophisticated techniques, and that depends very much on the infrastructure. But you can use drones, for instance, or any equipment to gather like the images, and with this image you can build what is called cloud of points. And with that and computer vision, that means basically artificial intelligence again, you can identify the assets and build a model. That's one thing, and that's worth it for complex infrastructure. And at Eureka, we have worked at that in some projects. But another option that maybe it's more handy, it's the measurements in the field. I mean, just going one day there or 2 days and taking the measurements, and with that you build a 3D.
Okay.
And that's that's what we are in an internal project. That's what we are doing at Eurecat. We have the living labs in Manresa and in Amposta. The one in Amposta is a new building, so we have the BIM model. Well, a new part of the building. We have the BIM model, and the one in Manresa is an old building, so we don't have it, and we are just experimenting how we can have digital twins of both, having and not having the BIM model.
Okay. Thank you very much. And this is our last presentation. I would like to thank all of the audience and also all of our invited speakers today, Irene, Raquel, Carolina, Regina, and Ginevra. And last but not least, for the iClimateBuild webinar, let's see if I make it work. And yes, so our next webinar is going to be on the topic of performance characterization of the building envelope by means of testing from material of full-scale prototype. And this will be our partner of Polito will present on this topic. But the date and the time, it will be defined later. And please follow us on iclimatebuild.eu and also social medias. And thank you very much for today, and thank you for stay tuned until the end, even though it's a little bit late. But you are welcome on the contact our speaker in case that you have any further question. So now I would like to close our meeting, our webinar. Thank you very much, and see you next time.
Thank you. Bye.
Bye.
Thank you. Bye. See you next time.